Welcome to lecture 2. So this lecture will broadly cover introductory material to machine learning, but I'll try to present it in a way that's computations centric. So what kind of computations do we have at different layers of a neural network? What is the ratio of compute and memory in the forward versus the backward pass? So things like that, we want to kind of gain a better intuition of what it takes to run a neural network on a computer. What does that computer even look like? Like what should the mental model of this DNN computer look like in my head when I'm thinking about it? So that's the purpose here. Some of this and most of it should be stuff you covered already in a machine learning course. But again, like I'm trying to look at it from this different perspective of computations. So let me share the screen. Share. Okay. Right, I think that worked. So yeah, so this is lecture 1. Just a few things to get out of the way. A0 is released on GitHub Classroom. So if you don't know how to get to A0, look at the discussion page. There's a link. You click on it, and it creates a GitHub repository for it. You should see your name on the class roster, and you should link your GitHub account to that name. If you don't see it or anything, let me know. And I should be able to link it myself if you're using your net ID as your GitHub username. So that should be fine. Any questions about A0 so far? It should be quite simple, very straightforward introduction. So I think okay. So yeah, please use the discussion if you have questions about it. So what have we been talking about so far? I mean, last lecture was mostly logistics, but we started talking about machine learning hardware and machine learning systems. And one of the things that we talked about was that we're not getting faster hardware for free anymore. We need to build our own hardware. We need to build domain-specific architectures to get improvement in hardware efficiency and hardware performance. And the main reason is because of the slowing down of Moore's law and the end of Dennard scaling. So these are two kind of terms. If you know anything about hardware, you should be able to kind of just say them and say, oh yes, because of Moore's law and Dennard scaling, I'm doing this. So I think part of the kind of benefit of this course is that you get to know a lot of this computer architecture lingo as well. If you're a CS person or a machine learning focused person, it's good to know this, this language of hardware designers and computer architects. And so if we're not getting chips that run faster through these scaling laws, we need to build our own hardware. We won't be talking about hardware yet, at least not in detail. That will happen next week in the next 2 lectures. But in this lecture, we will kind of try to develop a very simple mental model of a DNN computer, whatever that means, something that runs a deep neural network. So what does it look like? It has these 2 components. They're connected this way. So that's what we'll figure out in the next few slides. We will also go over just the forward and backward pass, first principles, very simple, and look at the number of computations and count the memory overhead of these passes in a deep neural network. And then in the third part of the lecture, we'll just go over common deep neural network layers. So you may know most of them already, but again, we will look at it from a memory versus compute perspective, and whether each of the layers and each of the components is memory bound or compute bound, and what takes more time, and things like that. So here is an example deep neural network, just to agree on some kind of definitions. I'll call each kind of computational block a layer, which isn't a great way of labeling it, because layer 2 and layer 3 here are in the same layer, so to speak. But let's call each one of those blocks a layer. Now, when I look at that neural network, what is it doing? It's looking at images, it's classifying them and giving me a class at the output of that neural network. And so when I look at it computationally, what should I be thinking about? So first, I should really think hard about the memory overhead of this neural network. So what is the size of the parameters? Does it fit on chip, on the chip that I'm using for computing? Does it fit in the external memory chip connected to that compute chip that I'm using? How long does it take to load these parameters from external memory? So that will include kind of knowing something about the memory bandwidth or the memory speed of this memory chip connected to my device. Okay, while I'm loading those parameters, what can I do something else? Can I overlap that loading of parameters with computations? Or is it just wasted time of like starting my computation? Is there reuse of those loaded parameters? So when I load those parameters on chip, can I use them multiple times, or do I use them once, then I throw them away and I need to load new parameters? So this is the idea of reuse. Again, similarly, during the computation itself, there are these huge tensors being produced. What is the size of those activation tensors? Do they fit on the chip, or do I need to spill them to external memory? How long does it need to remain a live value on chip? So is it used in multiple branches downstream and it needs to stay buffered on chip for a long time or not? And a lot of the activation, a lot of the stuff that pertains to activation is kind of very highly correlated, obviously, with the input, in this case, image size, and obviously the batch size as well. So how big is that? How big can I afford to make my input image resolution, and things like that? And so other than memory, the second thing is compute. So basically, how much computation do I need to make, and what is the parallelism in each of those layers? And that will help me figure out how to map those computations onto a piece of hardware. I remember at Samsung, we were optimizing a speech recognition model for one of those phones, and we cut the number of layers, the number of channels by almost, I don't know, by almost 40%. So close to half of the channels were pruned away. But the improvement that we got was just, I don't know, 20% or 23% in terms of actual runtime in the end. And what we figured out quickly is that the computation on those mobile chips was done in multiples of 32. So if we didn't prune the channels in multiples of 32, we were essentially paying for like a whole step of computation for 3 or 4 channels, whereas we could have been using that for 32 channels, if that makes sense. So basically, even the number of channels you have, do they map well on the number of compute elements you have on chip, is a consideration that you have to make. And as I said, you can, a very important aspect is also whether you can overlap compute with memory access. There's a question from James. Is that usually done with ablation studies for layer pruning? So it can be done with ablation studies. And usually what happens there is that you will find, you know, I don't know if you guys can see the board, but, and this doesn't work, okay. No. Okay, maybe we'll use our imagination. So basically, if you have number of channels on the x-axis and runtime on the y-axis, then you will see that runtime is like a step function. So every time we fill up our compute elements, so every step of 32, for example, you will see a spike in runtime, and then it stays constant because we're still filling up the same kind of compute array, and then it spikes again, and so on. So that was the case for this specific NPU that we were targeting, and that's why that's why it wasn't as fast. So yes, you can do it with ablations, obviously, and benchmarking, basically writing some micro benchmarks and figuring out how it runs, but that's treating the hardware as a black box. You can also kind of go and dig into the like the instructions of that hardware and see what is the vector size for each of the operations. Sometimes that's harder to do for complex hardware, but usually it maps fairly well. So data dependencies. So data dependencies are a huge thing in general computer architecture. There's this large portion of a CPU chip dedicated for obviously caches, but also branch prediction. If I have an if statement or any control flow statement, I need to figure out or predict where that branch is going to go so that I can fetch the right memory. In neural networks, that's not much of an issue. So data dependencies are few. As you can see in this example, layer 4 has a data dependency on layer 2 and 3. So most neural networks are feed forward. There are recurrent neural networks, but they're mostly feed forward. And sometimes when you have branches, you just need to wait for the branches to complete before you compute your next layer. But we will go through a few examples where data dependencies become important, especially in the management of on-chip resources. And so that's coming up in the later part of the lecture. Okay, so as I said, I want you to have a mental model of a computer when you're thinking about how to map a neural network onto hardware. And the general model that people have been using for the past 4 decades, maybe or more, is what's called the von Neumann architecture or the Princeton architecture. That's another piece of computer architecture lingo that you can kind of talk with when you're talking about computer architecture and machine learning together. And so, what is the von Neumann architecture? It's very simple, really. It's the model of a stored program computer. You have a program stored somewhere, and you load it. You load the data. You do some computation, and then you write back the data. And so what it looks like is, you have this central processing unit or some processing unit. It has some control unit, which is unimportant for us, but it has also the arithmetic and logic unit on it. And then it's connected by a low bandwidth bus to an external memory unit. And so when you're executing a program, you have to load the program data and the program instruction using this low bandwidth bus. And so that's typically what's referred to as the von Neumann bottleneck. And that's what limits most of the performance in computers in general. Why is that? Because you either need to wait for data to be loaded from external memory, or you need to wait to be able to write data to external memory or the program instructions themselves. And so what people have been doing to get around that, obviously with CPUs, is to create all of those big caches on chip to get data to be here. So they avoid the bottleneck by preloading the data and putting it right next to the arithmetic and logic units. And we'll see in the next week, actually, what most chip startups are doing for new machine learning chips is exactly that. They're just building chips without external memory units, and they're trying to make these chips as large as possible in some cases, and putting all of the neural network memory on the chip itself, very close to the computing elements. You might also have heard the expression processing in memory, where the opposite is being done. We're taking arithmetic and logic units and sticking them in the memory unit. And so these are all ways to get around this von Neumann bottleneck. But for our purposes and for today's purposes anyways, what we really care about here is, you have some arithmetic unit that does math, and then you have a low bandwidth bus, and then you have a memory unit which has all of the data. And so how do we get that data onto the chip that does compute? Yes, it's through that low bandwidth bus, but how do we do that efficiently? And so, so that's what I want you to think about when someone says computer or mapping something onto hardware. And now we'll try to figure out how to map a deep neural network onto this von Neumann architecture. So which part of that neural network is the program? Which part of it is the instructions? And which part of it is the data? So these are some of the things that you should keep in mind as well. Okay, so that's kind of a simpler cartoon of this von Neumann architecture. I also added this memory on chip because that's a very important consideration. Again, in CPUs, it's called caches, but we'll just call it a buffer or on-chip RAM or on-chip memory. So these are all kind of synonymous. So as I've been alluding to so far, it's very important to figure out whether your workload is memory bound or compute bound. So basically, does it take longer to fetch memory that I'm going to use in the computation, or does it take longer to do the computation itself, like the multiplication and the addition and all of that stuff? So obviously, this depends on a lot of things. It depends a lot on the hardware. So how fast is that memory bus? That will determine how fast I can get stuff on chip. What is the size of the operands? This depends on the neural network. What is the compute speed and parallelism available to me, right? What are the sizes of the intermediate results? Do they fit in this on-chip memory, or do I need to spill them out to external memory? And so on. So these factors can roughly be divided into factors that just depend on the hardware, and we won't cover those today, and factors that depend on the neural network, and that's what we'll be focusing on, right? So things like size of the operands and the ratio of computation in each layer to the memory of that layer. Yeah, so we'll focus on these DNN related factors. So a very common, I want people to kind of ask questions if they have any so far. I'm trying to take it kind of, I'm trying to slowly build this idea of how computations are made on a standard kind of computer architecture in your head so far. So, you have compute, you have memory, you have on-chip buffering, and we have a deep neural network that we want to execute. And so, a key technique to use when running computations is to try and overlap the memory access with the computation. And so here, for example, I'm showing like a time graph of compute and memory for a layer of the neural network. Let's just call it layer 1. And so first, what I need to do is to fetch the parameters of that layer 1 from my external memory, put it on the compute chip, so on chip, and then I can do the computation now that I have all of the data dependencies resolved. And then when I want to execute layer 2, what if layer 2 has a lot of memory and it takes a very long time to fetch that memory, to fetch that set of parameters from external memory? So in this case, that's what happens. You have lots of weights to fetch. So that stalls the computation of layer 2. And that will slow down your execution. So in this case, can people guess whether that's compute bound or memory bound in this case? Can someone just unmute and shout? Anyone? No?
Memory bound?
Great. Memory bound, yes. Great, okay, so people are awake. And lots of people wrote in the chat as well, good to see. So this is a memory bound layer, right? So we have a lot of stuff to fetch from off chip, and the computation is really fast. And so in this case, the hardware is being stalled for this amount of time. And that means that even if my hardware has a lot of multipliers on it, if it's a GPU with a million CUDA cores, it doesn't matter, because all of that extra speed won't really affect how fast my computation runs. So in this case, I would need to go and build a higher bandwidth connection to my external memory chip to make this workload faster. Right. So the opposite can happen, of course, when yeah, I have a question from Aman. Does this assume that there's enough space to store both the weights for layer 1 and layer 2? Yep. So that makes that very simple assumption so far, and we'll talk a bit about the chip memory in the next slide as well. So in this case, we have the opposite. So we have very few parameters to fetch from the external memory, but the computation takes a long time. And so now my memory bus is idle for a while. And so can people think, okay, is that a problem? Or, I'm fully utilizing my compute chip, so that's okay. So that doesn't matter. Or is there any problem that could arise because my memory bus is idle? Is this an inefficient architecture now, or is this perfect? Is this efficient? So I mean, think about it for a bit. Usually when we're optimizing hardware and we see an idle memory bus, we don't worry too much, basically. But what's actually behind it is that then that means you've over-designed your memory architecture and your memory controller. That means, and an over-designed memory controller means that it's fast for no reason. Obviously, if this happens in just one layer, then that's okay. But if this happens for all layers and you're always underutilizing your memory bus, that means that you have dedicated a lot of chip area for a very expensive memory controller. You've dedicated a lot of money to pay for this very fancy memory controller, but you're not really using it for this workload. And so that's just, chip area, that's power, and that's dollar value that's kind of going to waste. So usually it's not a huge issue if you see that and you're kind of happy, I'm fully utilizing my GPU or my hardware. But at the same time, you should keep in mind that I probably paid a bit too much for that piece of hardware, or it's over-designed for no reason. So James saying inefficient because, the memory bus. So James hit it spot on. It's inefficient because the memory bus is actually too large and power hungry. That's right. In this case, can we prefetch the next batch of parameters for efficiency? So, I mean, that's a good point. So why am I staying idle here when he is asking if I can just, fetch the parameters for layer 3 instead of remaining idle, and I can just get it early, and then I'll fill all of the bubbles in my memory bus. This goes to kind of the limited resource that's called on-chip memory. So the difference in size of on-chip versus off-chip memory for traditional computer architectures is orders of magnitude, right? Like you could have megabytes on-chip and gigabytes off-chip, so 3 orders of magnitude at least. And that's kind of comparing the size of caches to the size of DDR chips or something like that. And so usually what we do with deep neural network accelerators, and again, we won't go into too much depth of the on-chip buffering architecture in this lecture, but again, to further develop that mental model of that deep neural network accelerator, we usually use double buffering. And what that means is that if I'm currently executing layer 1, then I'll have layer 1 input parameters stored on chip. And as I'm doing that, I'm fetching the stuff for layer 2 in the second half of my buffer. So that's why it's called double buffering. And usually you don't have enough space to do more than double buffering, basically. I mean, sometimes you do, but usually that's kind of the simple mental model that I want you to have in mind. And the same is true for activations. Double buffering in this case means that you have both the input and the output of that layer being stored in on-chip memory, because that allows you to perform the computation really fast. And then you can use the output of that first layer as the input of the second layer, and so on. And so you keep kind of ping-ponging. So sometimes it's called a double buffer, sometimes it's called a ping-pong buffer, and it has maybe other names as well. So that's kind of what's happening on chip. It's quite a limited resource, and managing that is very important to the performance of neural networks, especially when you're designing your own architecture. And we'll talk a little bit more about this on-chip memory and scheduling algorithms to kind of take full advantage of them, both briefly in this lecture, but also in the mapping lecture later. So, okay. A question, yes. So, I mean, if I'm hoping that most of you trained a neural network on a GPU before, and so what does it mean when you get kind of a CUDA out of memory error, or your neural network doesn't fit on chip? So does it mean that the parameters don't fit in on-chip memory? Does it mean the parameters don't fit off-chip? Yeah, or is it both the parameters and activations that don't fit on-chip? So think about it for a minute, and I think I launched a poll. Just, yeah, give me your answer. There's a single right answer, by the way, for this one. I know the thing allows multiple. By external, do we mean VRAM? Yeah, you can call it VRAM, yes. In general, DRAM or external memory, yes. Okay, almost there, 75%. Okay, so the answers so far are all over the place. Okay. So yeah, so the majority of people actually picked 3, that the DNN parameters and activations don't fit on the GPU's on-chip memory. A lot of people also picked 1, that the DNN parameters do not fit on the GPU's on-chip memory. So in general, people are thinking about on-chip memory. And that's the wrong answer, actually. So when you get a CUDA out of memory error, that means that the HBM or GDDR5 chip attached to the GPU doesn't fit the model and the images used to train that model or do inference, right? Once you have the, yeah, so only 5 people answered the right, gave the right answer. It's, both your deep neural network parameters and the training data and intermediate activations need to fit off chip. You can always break down computations and tensors when you're doing the computation on chip. You can always break it down into finer pieces of computation, right? But you need the whole thing to fit in your memory system. And I mean, GPUs are quite unique because, GPUs have memory of what, maybe 10 gigabytes? Like very expensive GPUs go up to 32 gigabytes. Does anyone know why they have such a small memory capacity compared to CPUs that have typically, I don't know, 128 gigabytes or something? I think this laptop has 256 gigabytes or 512. So does anyone know why? Okay, James, yeah, so James answered. Faster speeds, Alexander and Nikki. So all of the answers are in the right kind of vein because this memory is much faster. And it's in memory systems, you always trade off size with speed, basically. So if you have a very large memory chip, it can't be really fast just because of the electricals of it and how it's organized and how it's connected to the compute and so on. And actually, it's not a CPU versus GPU thing. Some very high performance computers that are built especially for performance and have some very complicated instructions, they're still considered CPUs, but they have like 2 gigabytes of external memory, just because they need very fast memory to run these scientific applications, whether it's kind of climate forecasting or other things. So yes, out of memory means the external memory is full. Always remember that you can always break down computations and put them on memory to fit the on-chip memory. So, I mean, I gave you this very simple mental model of hardware based on this von Neumann architecture, where you have, external memory, compute, on-chip memory. But it's good to also know that there is such a big diversity of hardware out there, ranging from, a 1-watt chip, so a very low power chip, all the way to like a 300-watt GPU or something. There are dedicated chips doing things in a brand new way. There are non-von Neumann architectures. There are systems on chip where you have just a small part of the chip dedicated for a neural processing unit, and it shares the same memory system with other devices like a CPU and a GPU. So this is the case for kind of mobile chips. And so, so take this simple model with a grain of salt. That there are also other ways of doing this computation. But at the first order, still the same, the memory versus compute argument usually applies to most of these chips. Okay, so that's kind of the first part that I wanted to go over. If anyone has any questions at this point about, this mental model of a DNN computer, just let me know. Otherwise, we can move on to the second part of the lecture. So basically, we'll go back to kind of machine learning 101 and talk about kind of the forward and backward pass in a deep neural network. So let's talk about a single neuron. So we have, an input X and a parameter W, and they're being multiplied, and then there is an activation function, maybe it's ReLU or something else, and we have an output. So what happens in this small piece of a neural network in the forward pass? Okay, we are getting, we're doing one multiplication. So, multiplications are some of the most expensive operations, and that's what we'll be counting in this very simple model of a neuron. So we have one activation function and one multiplication. So now what happens in the backward pass? So we have kind of the loss gradient coming in, and then it propagates through the network. We have these local gradients in pink, and then we keep, using the chain rule and backpropagation to compute the gradients downstream during training. And then finally, in the backward pass, we compute the gradient that way. So we take the downstream gradient, we multiply it by the local gradient here, and then we multiply it by the local gradient here, and we're finally getting kind of the derivative of the loss with respect to the parameter at this weight value. And so if I count the number of multiplications here, and this is a very rough way and a very inexact way of doing it, but there are roughly 2 multiplications, right? Compared to the forward pass, which had 1 multiplication. And so we will take that as kind of approximately how expensive is a forward pass versus a backward pass. And during training, for example, after doing the backward pass, obviously you take that gradient and then you update your parameters with it. And this is basically one subtraction, which is much cheaper than a multiplication, and it only applies to the weights as opposed to all of the nodes in the graph. So in general, when we talk about forward pass versus backward pass versus gradient update, the backward pass is the heaviest part. The ratio is approximately 2:1, and the gradient update is typically very cheap. Of course, what I drew here and said it's a single neuron, that's not actually a single neuron. I was hoping someone would stop me. But this is part of a single neuron. So again, when you're thinking of neural networks, sometimes we go back to these biological inspirations, and I don't really like that because it's very disconnected from the biological part these days. But basically, we have more than one branch coming in. So we have these dendrites. Each one of them is a scaled input, right? And then we have an activation function and a downstream thing called the axon. So basically, here I'm showing just one dendrite connected to an activation function, whereas it should look more like this, where you have many dendrites or many inputs scaled by a parameter, trainable parameter, and then they're all added together, and then they go through an activation function. That doesn't really change the simple derivation that we went through, though. So, but now, at least for these boxes, we can say this is part of a forward pass and part of a backward pass, whereas the complete forward pass is actually a dot product between all of the inputs and all of the scale factors or the trainable parameters. And then they're all added together. So in the further reading, I'm linking to a blog post which looks right to me, that goes through a more detailed derivation of kind of the ratio of flops in the backward to forward pass or forward to backward pass. So I recommend reading that. It's not required, but I think it's fun to go through it and kind of do it with your own hand to grasp this idea of the you know, how much computation is going into each one. And there are some details, like the first layer has a different ratio. Convolutions will have slightly different ratio compared to linear layers and things like that. So it's good to go through that blog post. You'll find it in the end of the lecture. But at first order, when you're thinking about it, yes, the ratio is approximately 2 to 1. So, I mean, we talked about the flops ratio or the compute ratio of forward to backward pass. So what is the memory utilization ratio? So how much memory does the forward pass take compared to the backward pass? And, oh, can I relaunch? I can relaunch the poll. Okay. So I relaunched the poll. Let me know what you think in terms of memory utilization. So I mean, this is all we'll be talking about today: compute and memory. How fast does it run? How much memory do I need to fetch from off-chip? That's what we really care about as kind of hardware designers for deep neural network accelerators. Okay, so most of the answers came in, 84%. That's I can live with that. So the answers are split exactly between, you know, 2 and 3. 2 just 1. So 12 answers to 2 and 11 to 3. So and some people answered 1 and 4 as well. So I mean, the way I think about it is, well, I mean, I think the right answer is 1 to 1. And the way I think about it is that we have a computational graph. In the forward pass, we compute all the values along that pass, along that computational graph. In the backward pass, we're computing all the derivatives at these same points in the graph, right? So the ratio of the forward propagation is the same as the backward one, but the values are gradients instead of, you know, activations. And so during training, during the backward pass, we actually have double the memory utilization, just because, you know, we need to store the forward pass and use it in the computation of the backward pass. But I mean, in isolation, each one is taking roughly the same memory, if I'm not mistaken anyways. So. Okay, and I mean, one way to improve this is called model checkpointing. Which is quite a neat technique and works quite well. So if you don't have enough memory on your GPU, what do? You can skip some of, you don't have to store all of the forward pass. So basically in this neural network here, I stored the activations at the first input layer, but then I didn't store the activations at the hidden layer 1, and then I computed the activations downstream. And so during the backward pass, now I have a third of the memory that was required for the forward pass essentially saved or yeah, conserved, because I didn't store these values during the backward pass. And so so what does that mean? How do I compute the gradients at these points then? So what happens is that I just recalculated. So during the backward pass, when I need to compute the gradient here and I need the value of this activation, I would go back and use the input layer and recompute the value of that hidden layer to compute the gradients, and then I would throw it away again. And so that's DNN model checkpointing. And I thought I would mention it as a way that people are using to, again, trade compute for memory. Or in this case, trade memory for compute. So Okay, so that's kind of the brief section 2, just going over the forward and backward pass. And now we will talk about common deep neural network layers and important deep neural networks that we're using these days. What layers do they actually use, and what are the memory and compute properties of these layers? Again, if there are any questions, just type it in the chat or shout. So. Okay, so throughout this course, we'll focus on these 3 important applications. There are many more important applications in related to deep neural networks and deep learning in general, but most of the research is being done on those 3 domains, and most of the important applications are actually derived from these 3 domains as well. So speech, vision, and NLP. And so before we dive into the various layers or the various model topologies that are used in those application domains, we will just kind of see, okay, I mean, what is the state of the art in each of those? And so most of you may be familiar with this website, Papers with Code. I think Facebook made it to kind of keep track of all of the machine learning research and to see what's they basically have these leaderboards of what's the highest accuracy in each data set and things like that. And so I just copied those graphs from there. And in speech recognition, for example, we started 5 or 6 years ago with RNNs. People were using RNNs, mostly LSTM-based RNNs, to do speech recognition. This quickly shifted to 1D convolutions, which were found to work just as well in many cases, but were computationally much cheaper. Then kind of at the turn of this decade, transformers took over and in speech recognition, as it took over in many of the other domains, as we will see. And then now people are using a mixture of transformers and convolutions. And in the case of speech recognition, people are calling it conformers. In other domains, they're calling it something else. By the way, do people know what transformers are in general? Like if you type in the chat, yes or no, that would help me to kind of gauge whether people know. Yes, yes, self-attention. Yes, no. Okay, good. So some people know, some people don't know. So we will go briefly over them. Hopefully, if you have to, hopefully we'll have time. So one of the key things here is that we've been moving from more sequential and more sequential computations to more parallel computations, and that's I think influenced a lot by the nature of GPUs used for training. But also the scale of training. You need to finish your training faster to support larger data sets, which has also been the trend in speech recognition and other domains. And so that's the main reason why we're moving towards those highly parallel kind of architectures. And image classification. So the popular data set there is ImageNet. And so we started, with convolutions and fully connected layers or linear layers. And then we moved to fully convolutional or convolution only. Then again, transformers take over starting 2020. But then people, again, took a step back and thought about it a bit more. And now they're using a mixture of convolutions and transformers, or self-attention, basically, which is the main building block of transformers. So NLP. It's a very similar story to speech recognition, except that transformers stuck there. Convolutions were never really useful in the very sequential natural language modeling domain. And so we started with recurrent neural networks, obviously focused on LSTMs at some point, and then shifted to transformers. So yeah, I mean, we'll talk about these 2 important layers next. So convolutions obviously was a common one that came up in these important application domains. The other one is fully connected layers sometimes, but also just generally matrix multiplications, which are also the building blocks of self-attention and transformer networks. So we'll talk about those two layers in a bit more detail, just to make sure we're all speaking the same language and talking on the same page. And I have this somewhat blurry image of kind of the breakdown of computations in a simple neural network on both the GPU and the CPU. And I mean, what I want you to get from this picture, hopefully I'll update it. I don't think this is the best picture to show that. Basically, most of the time goes to the convolutions and the linear layers. So that's what this is showing on either the CPU or the GPU. Okay, so what is a convolution? Again, kind of taking a very simple introduction to what convolutions are. And we'll talk about 3D tensors in this case. So my input has, a height, width, and depth or number of channels C. I have filters, and these are the parameters of the convolution. They have, height R, width S, and the depth is the same as the input, and they have K of them. And when I perform a convolution between those two things, they produce an output that has H, W, and K now as the depth, which is the number of filters. So how do I perform a convolution? How do I compute a single output of that convolution? It's basically a dot product. So we've already looked at dot products in the, the single neuron view of neural networks. This is simply a dot product between a piece of the input that has the same shape as the filter and the filter. So, I sweep the filter across the input tensor. So I'm doing a dot product between all the values here. So multiplying all the values in that shape with all the values in that shape, and then adding them all up to compute a single value in the output. So just one number. And then, I sweep the filter across the image. So I go to the next part of the input. I go to the next part of the input that looks exactly the same as the filter. I do a dot product with that. And that's how I compute the second output. And then I repeat that for the third output and for the fourth output. So that's how a convolution works. And I mean, you'll notice that, I did all of these computations using a single filter that I have loaded on chip. So we're loading actually a very small amount of data and doing a lot of computations by sweeping that whole filter across the whole image. So to compute kind of the second channel or the second output layer of my output, I use a second filter and I sweep it across the image. And that's how I construct my output tensor during a convolution. So can you maybe think about it for a minute or two and count how many total operations do we have in a convolution? And we're talking about a very simple convolution. So we'll assume that the filter have odd sizes in the face, R and S are odd. And we have padding equal to R divided by 2 and S divided by 2. So that means basically I can perfectly sweep the filter across the image, across every pixel of the image, and stride equals to 1. So, so using these, symbols, H, W, C, R, S, K, what is the number of operations that I need to do? Multiplications and additions. If you think about it for a minute and maybe type an answer in the chat once you have it. Is this chat box frozen? No, no one wrote. Okay. Okay, I'll wait for at least one answer. So think of it as every time you sweep that filter across the input, you're doing multiplications equal to the number of values in that filter, and additions also equal to the number of values in that filter. And then you're sweeping that filter across the whole image, and then you have K of those filters. So Aman says on the order of H over R times S over W times C. Maybe. I'm not sure why you're dividing by W and R. Okay, I got at least one answer. So my answer is this. So basically, so Alexander, KHWC, KHWC, yeah. So yeah, I mean, so that's my answer, right? So basically, how many values do we have here? We have R times S times C values. And every time we sweep that across the image, we're doing 2 operations per value, right? So 2 times R times S times C, 2 times the volume of that filter. The two operations are multiply and add, right? So the dot product, you multiply each 2 values together, and then you add them. And then we're also sweeping that whole filter across the whole image, so multiplying by W, and then multiplying by H as well, to sweep the filter across the whole space. And then finally, we have K filters. So we repeat this K times, so multiplying by that last K. So James is asking, is the 2 from bias and activation? So I'm not showing bias here, actually. So you're right, a convolution layer also has a bias. I'm just, 2 is multiply and add. So multiply is 1, multiply plus add is 2 operations. So that's always the distinction. You'll get 2 ways of measuring compute in a neural network or in anything. It's either max, multiply accumulates, or flops. And here I'm counting flops. So each 2 flops equal 1 mac, because mac is by definition 2 operations, multiply and accumulate. So yeah, so that's the total number of operations. And if we think about the number of parameters, they're actually much smaller. They're just the volume of those filters. So R times S times C times K filters. And so, so this is an example of a very compute-bound operation. It takes very little time to fetch those filters from off-chip. And I mean, I took some time to actually draw them to show you the scale of how small they are compared to the number of computations, which are more proportional to the size of the input, whereas filters are usually much smaller than the size of the input. And so, so the computation takes a very long time, but memory access takes very little time. So this is compute bound. I mean, one way people have been trying to alleviate the compute bottleneck of convolutions is by using something called depthwise convolutions. And what that means is that every time I sweep the filter across the image, instead of producing 1 value in the output, I actually produce C values, or in this example, it's 3 values. And how do we do that? We do that by basically, so compared to a standard convolution where you do a dot product or a complete dot product between all of the input shape and the filter shape to produce 1 value. Here we are doing partial dot products. So we're doing a dot product between this red piece and this purple piece, and then we're storing it in the output. And then we're repeating that for the next channel, storing it in the output, and so on. And so this depthwise convolution has become a very common block in almost all of the efficient state-of-the-art convolutional architectures for image tasks or vision tasks, things like efficient net, mobile net, and so on. They're using that because this actually uses, this actually needs a lot less computation to produce the same output shape. And specifically, if a standard convolution is this many computations, then a depthwise convolution drops the C factor and becomes much more efficient. And if people have questions, let me know. But basically, this is an edge case of something called groups or grouped convolutions, where you can also have mixtures of this. So you can have kind of groups of 2 that's being combined into 1 output. In this case, each 1 piece of the filter is used to compute 1 piece of the output, but you can have 2 pieces of the filter, compute 1 piece of the output, and so on. So here, our number of groups equal to the number of channels. So does this now make the is this now compute bound, or does it become memory bound because I've reduced the computation so much? That's the question. So I said that this was one of the solutions of making convolutions faster, and it does make them faster. So you go from a very heavily compute bound layer to a less heavily compute bound layer, but you're also reducing the amount of memory that you're fetching from off chip. So it's still compute bound, typically on most chips, but it's much faster. And people have empirically shown that it works quite well when combined with something called pointwise convolutions. Okay, now let's talk quickly about linear layers or fully connected layers. And I put this after convolutions on purpose so that I can describe fully connected layers using 3D tensors first and contrasting them to convolutions as opposed to taking a matrix view of fully connected layers. So, I mean, I showed previously the weights of a convolution layer. They're also repeated k times, but for fully connected layers, each one of those weights, or the equivalent to the filter, is the same size as the input. So now you can imagine that's much more, many more parameters that I need to fetch from off-chip memory for a linear layer. And so if this is my input, and these are my weights with these shapes, and I have k of them, what is the size of the output of that fully connected layer? Restarting the poll again. Okay, so yeah, try to type in your answers. So I mean, I hope those polls are not annoying. It's just the only way for me to know whether people are kind of paying attention. Yeah, and I firmly believe that you kind of receiving a lecture for 1 hour and 15 minutes gets really tiring. So instead, you should also kind of do something more active. So hopefully, if people find them annoying, let me know. But okay, I'm surprised no one got the right answer so far. It's like, this is interesting. Ah, 2 right answers. Actually, can people see as the answers are coming in? Like, no? Someone is shaking. Okay, I can only see, okay. Because otherwise they just gave away the answers. Okay, so 27, 28, 70% participation, that's good. So, I mean, the answer is K, right? So if you think about it, the same way that you thought about a convolution, you're multiplying that whole shape with that whole input just to produce one output value. And then you have K of those. And so typically, you'll see a fully connected layer at the end of a CNN, for example, where we're just computing the class probabilities or the logits that would be used to compute the class probabilities at the output. So it's a massive reduction in from input to output size. And that's because of those huge weights that are connected to each one of those inputs. And what does that mean? That means that each weight is connected to an input, and then there's a huge dot product that happens between all of those things, and a big accumulation that happens between all of the partial values. Basically, we multiply this whole thing by that whole thing and compute just one value here, repeat it for k times. Of course, linear layers are also matrix multiplications, and not all domains require 3D tensors like the image domain. So what happens is that, I mean, if you used PyTorch before, there's this dot flatten kind of function. And basically, if we flatten that whole activation tensor that I showed here, it just becomes kind of a linear vector. And if I flatten each one of those weights into again, a linear vector, a single dimension tensor, then that's what it looks like. It's a matrix vector multiplication. We have k of those weights, we have a single activation, and we have an output activation. Now again, please type in the chat, is this memory bound or compute bound? And the hint is we have lots of weights, and then just one operation. So memory, compute, memory, memory, yes. So it is memory bound, of course. And it's actually, you're using each weight only once, and then you're computing one value in the output. And you have so many weights to fetch from external memory. And the way people usually get around that is by batching. So that means by adding multiple activations related to different inputs, obviously, and then you have a matrix multiplication. So depending on the batch size, you can actually hide most of the memory latency and turn this into a balanced kind of workload. Okay, so there are also obviously other layers in these neural networks, and some of the important ones are pooling, normalization, and activation functions. As I showed in that pie chart, we don't really need to think too much about those layers when we're thinking of just computation and memory versus compute and so on. But there are some pitfalls, and I won't go through all of them, but basically, for example, some activation functions can't be computed in place, and that means I need to compute a gradient before it and a gradient after it, which means that you're at least at that point of the neural network, you're doubling the number of gradients that you need to compute and the number of forward activations. So there are some details when you're kind of hyper optimizing a neural network that you also do need to take into account those seemingly harmless or seemingly benign layers. So more details in the book about each of those layers. Please go through chapters 1 and 2. And now on to the kind of the final part of this lecture. Hopefully I can make it in time. I think I have 10 minutes. And that's compound layers. So I think that's kind of just zooming out again after kind of zooming way in, looking at a single neuron and a single dot product, and then all of these primitives used in common deep neural networks. Let's zoom back out again and see how people are putting these primitives together to produce those compound layers, which are, again, now very common building blocks in neural networks. So I mentioned RNNs and LSTMs. I won't go into too much detail because just of the time constraints and the nature of this lecture. But basically, remember how I said data dependencies aren't a big deal in neural networks? They are kind of a big deal when it comes to recurrent neural networks. So in recurrent neural networks, this is an image of an LSTM layer. So as you can see within the LSTM layer itself, or the LSTM cell, we have all of these kind of more interesting connections, which means that there are some more complex data dependencies that you need to take into account when mapping this onto your computer, right? And the output of this layer is also connected back to the input of this layer. So if we look at it in terms of the number of time steps, or we do a computation of that LSTM, and then we take its output, we feed it back to the input, and we do the next time step, and then the next time step, and so on. So whereas this other axis is if we're stacking multiple layers to have a deep LSTM-based network. And so in RNNs especially, we do have those data dependencies that need to be taken into account. And there's a very nice kind of case study by NVIDIA on how to optimize these RNNs for a very parallel computer architecture like a GPU. So I recommend kind of going and reading this optional reading here to know a bit more about data dependencies or how they're handled on GPUs, both within a cell and between different LSTM cells. And now attention, which is the main building block of transformers. I'll briefly kind of go over what it is. So previously we had these encoder-decoder architectures, and they were mainly based on RNNs as well. So these inputs would go into different time steps of that RNN that I showed in the previous slide, and then it would go through a decoder and produce a translation. Here I used Arabic, which is my mother tongue, for the translation. I thought it would be fun, but it's basically a translation of, my name is Muhammad. It's written here. So what we see here is that there is kind of an information bottleneck. I get some representation of this input through various time steps, but I only transfer the output of the last part of the encoder, the last time step, to the decoder to do the translation. And so what people found is that this didn't work very well, and they instead created a different architecture that took the output of all of the input tokens, did some kind of weighted sum between those outputs, and then sent them to each of the inputs of the decoder. So when I'm basically finding the translation of each of the input tokens, so at each one of those outputs, I mean, I'm using information from all of the inputs. And this is very useful, especially in languages where, here I have just 2 words to translate those 4 words. So I actually need to take information from more than one word to figure out what each output is. Sometimes you also have, in different languages, the verb comes in different parts of the sentence. Like in German, sometimes the verb would come at the very end, whereas in English, the verb is usually at the beginning. And so having information from all of the inputs is very useful. And this is done through this attention layer, which is basically just taking all the outputs, multiplying them by a trained weight, and then summing them and putting them at each of the inputs. And so now I'm hoping this attention kind of looks simple. It's just a scale given to every output. So every output H, and then this trained scale factor alpha. And so if you read the transformers paper, the attention starts looking very different. And it looks a bit like this. There's a softmax applied to Q times K transpose divided by some constant, and then multiplied by V. So what are K, Q, and V, and what is all this stuff? And basically, what I'll say here is that it is a fast way of doing the same computation here, inspired by databases. So instead of doing this computation, which is quite sparse and needs to be repeated for each input, we are doing the same computation in vector form and computing something called the dot product similarity between projections of the input in different spaces. And so KQV correspond to key, value, and query, which is terminology that comes from databases. And if you read the original paper called Attention is All You Need, at least I didn't understand it from that paper. But there is this really nice Stack Overflow post that explains it very well. And it's just like a paragraph. And I highly recommend just clicking on this if you want to know how to go from the formulation of attention to the scale dot product attention. And again, if we talk about back to computations and what's happening here, the main thing that's happening is these purple blocks and the matrix multiplication, basically. And that's where we're spending most of the time here in transformers. And we did some benchmarking personally on some of the vision transformers, and the time was split almost evenly between the multi-head attention layers, which are basically this computation here, and the feed-forward layers, which are just fully connected layers. So I know that that's a very quick whiz through transformers, but what you should know from it is kind of why we're using attention roughly, how do we go from attention to the scale dot product attention, and reading this blog post or this Stack Overflow answer will help. And then roughly how computation is divided between the different parts of the transformer network. More compound layers. In CNNs, Inception was at some point the state-of-the-art network. And each one of those Inception blocks looked like this. So it was quite complicated. It had a bunch of branches and a bunch of dependencies. And while the Inception model itself is not that relevant anymore, this is still representative of an automatically designed layer. And so what I'm showing here, if this is my memory laid out linearly, how and when do I need to allocate different buffers, different pieces of data from that computational graph into buffers in that memory? And so this is a piece of work that we worked on during my time at Intel, and we found that using smarter kind of scheduling, so basically taking a different order through these computations here, so we can save a lot of space in our on-chip memory. And this is a key thing into optimizing or hyper-optimizing these neural networks for fast execution. Other important compound CNN layers that are heavily used now are the ResNet bottleneck block. And what that is kind of a 1x1 convolution, a 3x3 convolution, and then another 1x1 convolution. And the MobileNet inverted bottleneck block. The reason it's called inverted bottleneck is that it actually goes from narrow to wide within the bottleneck, and then to narrow again with a skip connection around. And people just found empirically that, again, that worked quite well, and it had way fewer parameters and was much faster to compute. And so these are two important layers as well. Yes, I made it. So and that's it. That's what I wanted to go through. So we kind of went through that mental model of what a computer looks like. It has memory, it has on-chip memory, and it has compute. There is a bottleneck called the von Neumann bottleneck when I'm getting stuff from external memory, trying to put it on my compute chip. We then went to just the single neuron view of neural networks, what happens in the forward and backward pass. And finally, we talked about common unimportant DNN layers, again, with this lens of compute versus memory. So you should now be able to kind of identify properties of different layers of a neural network. You should be able to analyze roughly the computation and memory overhead of different layers as well. In the next lecture, we will kind of go over specific metrics and specific hardware design techniques to basically take into account these compute versus memory trade-offs. And for this lecture, here is the further reading, and there are these very interesting and quick reads, which I highly recommend, but are not required. Okay, so I mean, that's all I have for today. And do people have any questions or any thoughts in the last few minutes? I'm happy to stay a bit after class as well if people want to discuss anything. Are the lecture slides posted on the website? Yes, I post them. I'll post them today. So lecture 0 was posted. There is a link in that Excel sheet, that Google spreadsheet that I have on the website. So, do skip connections have any consequences? Yes, of course. So, so the question is, do skip connections have any consequences on computation and memory? So a skip connection usually terminates in an addition. So, so it's added to the output tensor here. So that's a piece of computation. But we briefly talked about live values, or how long do I need to keep a tensor on chip because I'm using it in downstream computations. And in this case, I need to have enough storage to keep this whole thing on chip while I'm computing those intermediate layers, because I then need to use it for computation again downstream. So usually it has a lot of implications on this on-chip buffer management and on-chip buffer allocation. And that's why kind of it's important to manage these on-chip memory resources efficiently when you have multiple branches or skip connections and the like. Any more questions? Okay, if oh, one more. Specifically, are there nice, easy comparisons on computation, memory, cost for transformer versus CNN? I know transformer tends to be more costly due to the QK being O of n squared. So, so James is asking if there are nice comparisons between CNN-based architectures for vision and transformers. I think you mean for vision, because that's typically where CNNs are used. And yes, some scientific papers will go into and make that comparison, especially because, you know, usually if you're writing a paper, you kind of see what the baseline is. The baseline is efficient net, which is a CNN. Then you have to kind of beat that baseline on one or two metrics. So usually papers will have these comparisons now, and maybe I'll paste them in some future slides. Transformers are approaching the same compute and memory footprint as convolutional neural networks in general. It really depends on the number of tokens you use in the input, so how fine you split your input image. And it also depends on this attention layer. So people have been replacing this attention layer with things like even FFTs, and there are papers that are replacing it with low rank approximations of attention and so on. So I mean, one thing I should have said about this attention layer is that it's quite sparse and easily compressible. But when you compute it in a dense fashion, it scales quadratically with the number of input tokens. And so there's a limit on how many input tokens you can send in. In terms of CNNs, that obviously corresponds to the resolution of your input image. So I hope that made sense, James. But there are nice comparisons. And actually, so maybe in assignment 1, this is one of the things you can do. I know assignment 1 isn't released yet, but you will do a lot of comparisons between networks. And if you're interested in specifically transformers versus CNNs, then you can choose those two networks and compare them. Okay. All right, if there are no more questions, that's all I've had today. Thank you for your attention. And I will just stick around for a couple of minutes in case anyone has anything they want to ask.